Hello again, it is Mrs. Gunlock, and I am doing lecture 3 of 3 about gases. Here we go. We were just talking about temperature and what it means, and how temperature is the average of the kinetic energy. And that has a relationship to the speed of the particles as they're bouncing around, which it's actually surprising how fast gas particles move. They move like 1,000 miles an hour bouncing around. If the temperature is the average kinetic energy, and we've got this formula Ke equals 1/2 mv squared, then this formula is telling you the average energy, and therefore you can figure out the average velocity that the particles are moving. And so you can actually calculate like how fast is this particle moving at this temperature. And the other thing that's related is the mass. If it's really heavy, for the same amount of energy, it's going to be going more slowly because the mass and the velocity multiply together to give you the Ke. And the average is called the root mean square speed. You're familiar with the use of mean as average from math class, I presume. And the unit that you get out of this is meters per second. And then, crazily, the formula to specifically figure out the velocity of an individual particle based on its temperature is this, which is URMS, root mean square, velocity, the speed, which they're using a U for. Maybe that's a V, but that looks like a U to me. Anyway, why didn't they use a V? I don't know. Neither do I, little starfish. But the root mean square speed is equal to the square root of this whole deal, which is 3 times R times temperature divided by big M, which is the molar mass. And it's important to remember that since this is an energy-related formula, we're using the 8.3145 version of R instead of the typical one, the 0.08206. So this is I think the second formula that uses this one that we're going to learn. I think that's it, just this one and what's the other one? The one from the previous page. Anyway, so that's that R. The temperature has to be in kelvins. And it's important to understand the concept of mass and velocity both playing a part in the kinetic energy. That if you've got heavy particles and light particles and they're at the same temperature, the light particles are going faster and the heavy particles are going slower. They have the same amount of energy, but the fact that they're heavy, the fact that the heavy guys are heavy means that that energy is pushing a larger amount of mass around, so they're not going quite as fast. So that's particle speed. Woo! And then next topic in our little potpourri of final topics is collecting gases over water. One way, actually a really good way to collect gas from a reaction is to have the reaction happening and have like a tube and it's in the water and the bubbles come up through the water and then you collect them above, and then you don't accidentally get like random air in there. So here we've got an Erlenmeyer flask with some hydrochloric acid and a block of zinc. And if you know about this reaction, you'll know that the zinc is going to bubble and make zinc chloride and hydrogen gas. And that hydrogen gas will bubble up through this liquid and collect in this balloon up here. Let's say this is a balloon. So hydrogen gas fills this balloon, and you're like, hey, this balloon contains only hydrogen gas. Well, it doesn't actually, because the fact that you bubbled it through the water meant that a little bit of the water evaporated into your bubbles on the way. And that means that the gas is slightly moist. It's got a little bit of water vapor in there. And if you recall, Dalton's law of partial pressures says that the total pressure is the combination of the pressure contributed by by both of these gases, the hydrogen gas and the water vapor here. So it's important to, when you're doing your calculations based on an experiment that's like this, collecting gas over water, you have to subtract off the contribution made by the moisture. And there's a little table that tells you what the vapor pressure of water at particular temperatures is. And let's say this experiment is taking place at room temperature, so 25 degrees Celsius. You go and you check the table and it says, hey, at 25 degrees Celsius, the vapor pressure of water, which is the pressure that you're going to get of it evaporating off, is 23.8 millimeters of mercury. So what you do is you go, okay, well, my total pressure is 1140 millimeters of mercury. 23.8 of those millimeters are being contributed by the water. So the pressure from the hydrogen is 1140 minus 23.8. And that solves for X down here. And now you've got your pressure contributed from hydrogen, and you can go and use that in, say, the ideal gas law to figure out how many moles of hydrogen you got out, because you know the P and you know the volume of the balloon, hey balloon, for V, and you know R because you always know R, and you know T because it's 25 degrees Celsius. So you can figure out how many moles you made, and then you can do stoichiometry, and you can just do all sorts of fun things. But you will see questions that say, you collect this over water, da da da, and they just totally blow right by it and assume that you will go, oh, over water. Why, I will subtract off the contribution of pressure made by the water that's in the gas. And you have to remember to do that, because otherwise you're just going to be slightly wrong, and then you get -1. Ooh. All right, so that's collecting gas over water. And next little topic, we've got effusion and diffusion. You've probably heard of diffusion, but you probably haven't heard of effusion. And the one that you're familiar with is diffusion. And this is when, say, you take a can of hairspray or Lysol or whatever, and you spray it in one corner, and then 5 minutes later, people down the hall are like, did someone spray hairspray? Let's see, what else is diffusion? Or like my husband, who set his peach fuzz on fire when he was in the 6th grade. You should ask me about that. A couple of minutes after that had happened and the teacher didn't see, someone across the room from him goes, does someone smell burning hair? And he's like, oh, yeah, I do smell that, huh? So that's diffusion. That's one gas that slowly travels across and winnows its way through another gas. Effusion is slightly different, even though it rhymes. And this is talking about if you've got a helium balloon versus an air balloon, like the kind that you blew up with your breath, how fast do they deflate? And what's happening is that the helium particles are going through the rubber, and the air particles are going through the rubber. And the question is, well, which gas particles can escape faster, and what's the relationship between the rates of escape and the size of the particles? So effusion is gas particles escaping through a tiny hole in their container. So for example, this is supposed to represent a flask, a glass flask with like a stopper here. And if the glass flask has a tiny hole, and it can be really tiny because helium is very small, then the gas will slowly leak out through that hole. And we have got a formula that describes how fast that happens, comparing two different gases. So, and this depends on whether the particles are moving fast. The more speed they have, the more frequently they hit that little spot by the tiny hole, and the more frequently they hit it just right so that they can escape. And if you remember back up here with particle speed, the two things that the thing that matters is what the mass of the gas is, because if it's a heavy gas, it's moving more slowly, and if it's a light gas, it's moving more quickly. So looking back at that formula, kinetic energy equals 1/2 mv squared, what that says is at a given energy or temperature, a heavy particle, that's your heavy mass, for example, moves slowly. So you've got a big value for m and a small value for v. At that same temperature, a light particle, a small value for m, moves quickly, a high value for v, and they multiply together to give you the same kinetic energy. What this means in terms of effusion is that small gases can leak out of holes very quickly, and large gases can leak out of holes quite slowly. So if you remember Plurk from last year, he was definitely not a helium balloon because he lasted for months. Also, that must have been a really high quality rubber balloon because we were very surprised how long he lived. But if that had been a helium balloon, he wouldn't have lasted that long because the helium can get through those holes faster. So the formula is R1 over R2 equals the square root of M2 over M1. And that's sort of retarded, but let me explain it. You've got R, which is the rate of effusion, and that's usually, it's given in random kind of different units because there are 2 R's here and the units end up canceling. So it's got to be volume per time. It can be liters per minute or milliliters per week or whatever. Like, it's got to be volume and time. They have to match. If they don't match, you have to make them match. And the molar masses are, the big M here is molar mass again. And what you need to notice is that is 1 over 2, rate 1 over rate 2, and mass 2 over mass 1. They're flipped. It's not 1, 2, 1, 2. It's 1, 2, 2, 1. It's going to be real easy to get those backwards, so that's why I'm making a point of it. And this whole side here is square rooted, not just the top part. So that's M2 over M1, then take the square root. And what this does is it compares the rate of effusion to how big the gases are. So they'll say, hey, you have a gas that leaks at this rate. You have this rate for this gas. What about this gas? How fast would it leak? Gas number 2 here. So you put in the molar mass of that gas and you go, well, R2 is equal to 10 liters per minute. That's really fast. Must be a big hole. So there you go. That's the relationship between leaking and size. All right, last topic, van der Waals equation. You may have heard of van der Waals forces, which we're actually going to hit later. But whenever they talk about geckos and why they stick to the ceiling, they'll say something like, geckos can stick to the ceiling because of van der Waals forces. And then they move on and you're like, what are the van der Waals forces? There was this dude, his name was van der Waal. And he was really interested in the way particles are attracted to each other. So he did some stuff with gases here, and he also did some stuff with like condensation and why gases will condense and be attracted to, the particles will attract to each other at colder temperatures, and just in general, that's what he studied. He pops up twice, and they're kind of related. And van der Waal was thinking, so this ideal gas equation, it has these assumptions that say, number 1, that the particles don't have any volume. Well, that's dumb. Of course they have some volume. It's not big, but it's a little bit. And then the other assumption that he kind of challenged was the assumption that the particles are not attracted to each other or repel each other at all. Well, that's kind of dumb, because they do. And depending on what gas it is, it's going to be larger or smaller, or attractive and repulsive. Especially polar gases like ammonia are going to be quite attracty to themselves. And so, the ideal gas equation doesn't really describe them as well. And large gases, for example, do actually take up some volume, especially if they're really crammed together. So if you've got a high pressure system with a large gas inside, you know, maybe that gas takes up 1% of the volume. 1%. Yeah, normally it's really, really, really small. So van der Waal was like, okay, so the ideal gas equation says these two assumptions. Let me fiddle with that equation to make it describe real gases. So he took PV equals nRT and then said, okay, pressure is an assumption. You're assuming that the particles are not attracted to each other at all, and that they're just hitting the walls of the container, and that it doesn't matter what gas it is. That's not true. So I'm going to say that actually pressure, and then I'm going to correct for the attractions of the particles. So the ideal has got A in it. And it's kind of funny because he's like, it's pressure and something. And he didn't really, like, he didn't know what the value of it was because it's different for every gas, but he just kind of changed the equation and said there's going to be pressure and then something to correct for the fact that this is an assumption. So P is here, and then times V, and he said, okay, for volume, I need to correct for the assumption that the particles don't take up any space. So I'm going to subtract this off. So we've got volume minus B, you know, the constant that accounts for the fact that they have some volume. So he just kind of stuck them in there and said, I'll figure out what their values are later, but I'm going to fix the assumption about attractions here, and I'm going to fix the assumption about volume here, and that equals nRT. So this is just kind of a funkified version of PV equals nRT, with you stick in little values in order to account for the pressure and the volume changes. And the A's and B's are listed in tables. People took this equation and they went and found the actual values for all these different gases, and then calculated what A and what B was, because plain old PV equals nRT says that all gases will have exactly the same pressure and volume and number of moles and temperature. That's not actually true. They do vary very slightly. And so people went and they calculated A's and they calculated B's, and there's a table in your book that tells you what they are. So what's important really for this concept is when are gases behaving ideally, and when are the gases behaving strangely, and when are they most like an ideal gas, and the conditions under which a real gas is most similar to an ideal gas is when it is hot and when it is low pressure. And the reason is because when a gas is hot, the particles are moving really fast. That's because of this formula up here. When a gas is hot, here's your T, the particles are moving really fast, your velocity here. And when the particles are moving really fast, they whiz by each other before the attractions have really a chance to make a big difference. So you've got these particles that are going so fast that the attractions end up not mattering. Hey, that's what the ideal gas assumption says. So hot is very ideal. When it gets cold, you've got the opposite. You've got these particles that are going more slowly, and they're like, hey, I'm attracted to you. Ooh. And they get closer. So hot and low pressure. Low pressure gases, when you've got something under low pressure, the particles are pretty far apart. And when particles are far apart, it means that they're not contributing a large percentage of the volume of the container. If you squish everything down so that you have a high pressure system, you do have particles that are close together, and they're taking up a significant, and by significant I mean like 1%, a significant volume of the overall volume. So it's important to remember that hot and low pressure are good conditions for the assumptions to be sort of true. And so that's why when it's hot and low pressure, the ideal gas law works better. When it is cold and high pressure, the ideal gas law works less well. And you've also got to consider that when something is cold, when you take a gas and you cool it down, what does it do?
It condenses.
That's a very good answer, Starfish. It condenses, and when a gas condenses, what's happening is that the attractions are so strong that they're actually now sticking to each other. And so, do liquids follow the ideal gas law very well? No. All right. So there you go, a potpourri of 4 little ending topics for our gas chapter, and go ahead and answer your questions on the back of this page, and I will come back and answer them, and you can see if you are right. All right, question 1. Calculate the root mean square velocity of oxygen gas molecules at 300 Kelvin. All right, so that's going to be this formula. There's only one number there. Look at that. Whee! That's going to be U RMS equals the square root of 3 times R times T over M. All right, and that's going to be the square root of 3 times, and it's important to remember this is an energy related formula, so your R is going to be 8.3145 times temperature, which is 300, and divided by your molar mass of oxygen molecules, which is important to remember that oxygen molecules are diatomic, whereas oxygen atoms are just atoms, monatomic. So oxygen molecules have got a molar mass of 16 times 2, so 32.0 grams. You multiply, divide, and square all that out. Square root that out, and you get, let's see, well, temperatures are always unreliable in terms of sig figs. I'm going to go for 3. 15.3, and then the unit for this velocity dude here is meters per second. So, bam. All right, question 2. Helium is collected over water at 25 degrees Celsius and 1 atmosphere total pressure. What total volume of gas must be collected to obtain 0.586 grams of helium? This is over water, which is requiring you to use a little bit of Dalton's law of partial pressures. So P total equals P1 plus P2. So what we've got is the total pressure is 1.00. And then P1 is the helium, which we don't know, and the water, which they were really nice and they looked up the value in the table for us, is 22.8 torr. Torr! Oh, they're so mean. Don't you think they're mean? Torr is 22.8, and then you would divide by 760 in order to get atmospheres. And P1, which is the pressure of helium, ends up equaling 0.97 atmospheres. So that we are about to use in a second. What total volume of gas must be collected to obtain 0.586 grams of helium? That's going to be PV equals nRT. Pressure, we know, yay, 0.97. Volume, we are looking for. N, we don't quite know yet, but we'll know it in a second, because N is going to be equal to, we've got to convert your grams of helium into moles of helium. So that's 0.586 grams of helium. Grams of helium is 1 mole of helium. And that gives you 0.1465 moles of helium. So N is 0.1465, R is 0.08206, and T is 25 degrees Celsius, which is 25 plus 273, which is 298. And what you get is V equals 3.69 liters. All right, 3. Which gas would effuse faster, neon or carbon dioxide? How much faster in percent? And the thing that you have to remember is the reason that gases effuse faster is because they are small. So you need to consider how big these guys are. You've got neon with a molar mass of, oh, I don't know, something, 20? Dear neon. 20. The molar mass of 20 grams per mole, and carbon dioxide, which has got a molar mass of 44 grams per mole. So what we have is a small gas and a big gas. So which one effuses faster? They're asking which one travels faster, which one has a higher velocity and can hit that little hole more frequently. That's going to be the small guy because of 1/2 mv squared. If you have less mass, you have more velocity with the same kinetic energy. So how much faster in percent? We're going to need to compare them. How did I do that? Right. We're going to compare them and assume that one of them is just a rate of 1. So rate versus rate equals square root of m2 over m1. If you're comparing these two gases and you don't really have a rate of effusion for one of them, you can just say that the first guy has got a rate of, say, 1, and the second guy, we will be able to compare him. If this guy is going at a rate of 1, and that's rate 1, that's for neon, and this is carbon dioxide, so this is carbon dioxide and neon. Carbon dioxide has got a molar mass of 44, and neon has got a mass of 20. So you work that out, and you do 44 divided by 20, square root, second answer. So that's 1 over R2 equals 1.48. So R2 equals 0.67. So that means that when neon is going at a rate of 1, R2 is going at a rate of 0.67. So how much faster is neon going? It's going a third faster, it looks like. So 0.67 over 1 minus 0.67. No. The difference. Oh yeah, 1. This is percent difference. So it's 1 minus 0.67 over 1 equals 0.33 times 100 equals 33% faster. There we go. All right. Question 3, part B. Calculate the rate of effusion of phosphorus trihydride molecules through a small opening if ammonia molecules can pass through that same opening at a rate of 8.02 centimeters cubed per second. So this is just a plain old Graham's law of effusion question. So rate 1, here's particle 1 and here's particle 2. So for 1, we don't know this one, the rate of pH 3. The rate of ammonia is 8.02, and square root ammonia and that guy, and then the molar mass of ammonia is 14 plus 3, so 17. And phosphorus, what is your mass? It's 30.97, so that's going to be 33.97. And that gives you the rate of pH 3 is equal to 5.67 centimeters cubed per second. And to consider whether that makes sense, the small molecule is ammonia, the large molecule is pH 3. The small molecule goes faster, and it's showing 8.02, and the large molecule should go slower at 5.67, so that is correct. All right, question 4. Arrange the following in increasing order of your best estimate of values for B for van der Waals equation. What physical property is reflected in this arrangement? So you've got to remember what B is. And in order to do that, you might as well remember what A is. A is the correction for attractions. B is the correction for volume. So what we've got is basically saying B, your correction for volume, which one is going to be real small and which one is going to be big. And that's going to be based on the size of these particles. So small, the smallest, I'm going to say is helium. And the big one is this guy, SF6. That is an enormous gas. So we got you and you. Now these three, we've got carbon dioxide, water, and hydrofluoric acid. That one's next in terms of size. Now for water or carbon dioxide, water's going to be smaller because it's got a mass of 18 and carbon dioxide has got a mass of 44. So water and then carbon dioxide. And if you go and look in your book, I think that's a correct list, although I'm not sure they list all of them. So what that means is that the gas that is most similar to an ideal gas is the one with a small value of B, because there's not much of a correction. That's going to be helium. And the one that is least similar to an ideal gas is the one with a giant correction, is going to be sulfur hexafluoride. So the physical property that's reflected in this arrangement is size, and increasing size. All right, calculate the pressure exerted by 1 mole of xenon gas using van der Waals equation, and the values on page 423 in your Brown textbook. So in a 100-liter container and a 1-liter container. Now you need to consider that, I don't know what you need to consider. All right, A, in a 100-liter container, you do need to consider that this formula is really hard to write down because there are a lot of pieces to it. What's nice is that this is 1 mole, so you can take out all the n's. So what you end up doing is you've got P plus AN squared over V squared. I'll take them out in a second, wait for it. V minus NB equals nRT. Since the n's are all 1, so to rearrange this, you need to rearrange it so that P is by itself. So you can have P equals RT over V minus B. So that takes care of this part. And then this part gets subtracted, minus A over V squared. So put in your values for that, and you end up with R, which is 0.08206. Your temperature, which is 23 degrees, which is 296 Kelvin. That's a 6. 296. And V minus B, your volume is 100. And your B, if you go look in your textbook at the value for xenon, it's 0.051. Minus A, the value for A is 4.19. And again, over your V squared, 100 squared. You work all that out, and you get 0.24 atmospheres. The second one is the same, except that you replace the 100 with 1, so you end up with 0.08206, 296. 1 minus 0.051. Notice that this is much more significant when you're subtracting it off of 1 liter than when you're subtracting it off of 100 liters, and that represents the fact that your B, your correction for volume, is more significant when the gases are squished and at higher pressure. So we should be assuming that our P is going to come out bigger here, minus 4.19 over 1 squared, and you end up with 21.4 atmospheres, which is much larger, and there you go. Bing, bing. All right, and then under what conditions of temperature and pressures do gases behave least ideally, and why? Least ideally is going to be cold and high pressure, because most ideally is hot and low pressure. And the reason that cold is very non-ideal is because your gas is almost condensed, your particles are moving slowly, and when they're moving slowly, the attractions matter because they have a chance to pull towards each other, kind of keep each other away from the walls of the container, and so the pressure is lower. And the high pressure, when you have high pressure and it's cold, which is sort of hard to accomplish, so high pressure, what you've got is particles that are really squished. They are close particles. And so the volume of particles is important or non-negligible. Bam. Okay, that's it. Thanks, folks.